Our first speaker is Rishab Kothari. He's a graduate student researcher at Stanford University. He has spent a considerable period of his study life working on energy materials, the most recent being advanced energy storage. He is passionate about the clean energy revolution and wishes to be an integral part of it. Rishab enjoys sharing his thoughts on the potential bottlenecks renewables could face as they become the next ubiquitous source of energy.
Hey, thank you so much. Thanks, Emmy, for the introduction, and thank you all for coming over here in order for this talk. As we know that the energy landscape is definitely transforming. As we are moving from fossil energy to the more renewable source of energy, we are having a lot of transitions which are taking place right through this process. And in my opinion, I feel batteries are there to play a very crucial link. And it is indeed set to be the road to renewability. And through my presentation, I'm basically going to be talking about how batteries have transformed over the years, as well as a few of the integral roles it is going to play as it becomes the next crucial link in the form of energy. So just starting off, a brief introduction about what the talk is going to entail. I will start off by talking about what is a battery, its importance in the energy landscape, the key parameters which we talk about when we discuss different battery chemistries, the materials used in batteries, and one of the key questions which are very often asked, is there enough lithium to power all the batteries that we speak about? And a few concluding statements about where my opinion lies on this important topic. So definitely starting off, what is a battery? A battery in itself comprises of four major components. You have the anode, you have the cathode, you have the entire space in between, which is the electrolyte, and you have a separator which separates the anode and the cathode, basically. What is the cool thing of batteries and why is it so prominent? The essential in this is that when you have the ion which moves from the anode to the cathode, the separator only allows the ion to move past it. It forces the electron to take a route via the circuit. And that electron is the source of our energy. We are able to use that electron to power our devices. The second cool thing about batteries is that this process is reversible. So when I need energy, I can literally make the ions move from the anode to the cathode and extract charge from it. When I don't need energy, I can push it back the exact same route and I can store energy in batteries. The reason why this is a truly complex system is because as we try optimizing the anodes, we have to optimize the cathodes, the electrolyte, and the separator, because this entire system has to work in unison in order for the product, that is the battery, to work efficiently. Each of these need to be optimized independently as well as collectively as a system. And that's what makes batteries a truly complex system. Moving further, why is batteries the crucial link in the energy landscape? And I have bucketed this down into four major subsections. The first one is the small subsection, which we talk about are wearable devices, like the Apple Watch. And as we want these devices to be more compatible with our bodies, we are pushing the thrust of battery technology to an extent where we require batteries to be flexible. We want it to conform to our bodies and our emotions. And that pushes the realms of battery chemistry. We need specific parameters to be established in order to allow for this flexibility. The second one, which is the medium, which is pretty much there in all our phones. One interesting fact is approximately 40% of the width of our iPhone is because of the batteries. And as we push battery technology, as we push and we want thinner devices, we will need to push battery technology to make thinner battery devices. That means we should be able to get our specific charge right now with a smaller size. The third one, which is the large section. This is the most spoken about section right now as it is becoming commercialized rampantly. It's the electric vehicle market. Interestingly in this, about 55% of the cost of the electric vehicle is because of the battery pack. And as Tesla and other companies out there try to drive down the cost of electric vehicles, it is going to become imperative to lower the cost of batteries. And that, once again, is going to lay a thrust on battery technology. The fourth and the final one is the large, or the huge bucket, which I term it as. This, in my opinion, is the most exciting of the lot. It is something which is uncharted and it is still to be penetrated deeply into. It is large-scale energy storage. The cost of acquiring solar energy and wind energy and converting it to electricity has been driven down drastically over the years. The key parameter, which is the remainder factor, is how do we store this charge when we are not able to get sunlight and when we are not able to get wind. And that is where batteries are going to once again play a very crucial link. Moving down, what are the key parameters we speak about when we compare different battery chemistries? The first one is energy density, which can be categorized under two subsections. The first one is energy per weight of the battery, and the second one is energy per volume of the battery. For example, you want to be able to store maximum amount of charge in the minimum amount of weight and volume. As I had said, about 40% of your iPhone is your battery. In order to make that thinner, you will require higher energy per volume. And that is what is going to drive down the thickness of your devices. The second one is life, which is categorized under two subsections once again, which is calendar life and cycle life. For example, when we have a large-scale energy storage set which is put up, we cannot change that regularly. We need it to have a long cycle life as well as a long calendar life. And that makes this a very essential parameter when we compare battery chemistries. The third one is safety. And this is something which has been spoken about excessively because of certain cases which cropped up in the past. There is a lot of impetus in the research environment which is being laid on the safety of battery chemistries. People are working on solid electrolytes, as well as drastic measures are being put forth in the testing mechanism. For example, the nail test. And batteries which are able to survive this nail test, those are the battery chemistries which literally are used in commercial applications. The third one is temperature performance. You want your battery to perform as efficiently in the extremely hot and humid weather conditions of Texas, as well as work in sub-zero climatic conditions of Alaska. And that once again becomes an essential parameter. The fifth and the most important one, which I personally feel for, is the cost of batteries. As you want to make batteries ubiquitous, you need to drive down the cost so that people can afford this technology and believe in it. And that, in my opinion, is going to be one of the key determining factors as we move and transition to renewables. This is just a quick comparison about the various battery chemistries and the way it has transited over the years. The lead-acid battery was something which had started off right in the inception of battery technology. It has been there since 1960s. It is there in your vehicles right now, even though it's not an electric vehicle. The disadvantage of lead-acid, even though it was cheap, it had a very low cycle life and it had a low energy density. And that's when lithium-ion came in and really swooped up the market of the energy vehicles, because you were able to store a lot more energy in lesser space and in lesser weight. The only drawback of lithium is basically the cost. And this is something which I would be delving on in further detail as we move down in the presentation. Why exactly has lithium been the most winning of all the battery chemistries so far? It is because of the element. The lithium element in itself is a really special element. It is the third element in the periodic table. It has a small size, which makes it easy for it to be intercalated or exchanged between the cathode and the anode during the charging process and the discharging process. The second thing, it is lightweight. And as I said, you would not want a heavy battery. And therefore, the lightweight of lithium once again makes it a viable element. The third reason is it's a highly reactive element. And the final one, the fourth one, is that it has a high negative voltage, which allows you to store a lot more charge in your battery pack when you're charging and discharging the battery. So just talking about the cathode and the way the cathode has transited and the various materials which are used in cathodes over the years. The first one was the lithium cobalt oxide cathode material, which had been discovered in the early 1990s. It is an intercalated structure. It is basically a layered structure of cobalt oxide, and you have the lithium ions which are intercalated between these layers. As you charge your cell, you have the lithium ions which get intercalated and settle and form a stable compound within the cobalt oxide. And when you discharge it, these lithium ions are pulled out from these layers and sent to the anode. The lithium cobalt oxide definitely was a very good cathode material and was tried to commercialize, but the cost of cobalt restricted it. And therefore you have the next one, which was the lithium manganese oxide, which is used in the Nissan Leaf, in the initial versions of the Nissan Leaf. It is used out there, and the advantage is that it's a spindle structure. It allows two-dimensional motion, two-dimensional flow of the lithium ions as it is exchanged from the cathode to the anode and vice versa. The drawback of this was that you did not get a good cycle life. It does not last as long as the other cathodes. That's when you have the third generation, which is the lithium nickel cobalt aluminium oxide cathode material, which has been heavily commercialized by Panasonic and Tesla over the years. This basically leverages off all the advantageous elements and ensures that the cost is driven down by using the least amount of cobalt. So as you can see, the split is 85% nickel, 10% cobalt, and just 5% aluminium in order to stabilize this entire compound. And that is why this has been, so far, one of the most successful battery cathodes when we consider the electric vehicle market. What's new with the cathodes? This is the lithium nickel manganese cobalt oxide cathode material, which is definitely down to play a major role as electric vehicles become ubiquitous. This, once again, as the NCA chemistry, utilizes the advantages of the nickel, the manganese, and the cobalt elements. The nickel element basically allows you to get a higher charge density. That means you can travel further distances on a single charge. The manganese-rich composition maintains battery cyclability. It lasts a longer amount of time and it improves the safety of the battery. The cobalt-rich composition basically allows you to be able to charge faster. So that means when you go to a fast charging station, if your battery pack takes about 10 minutes to charge, if you have a high amount of cobalt, it may take you about 5 minutes or maybe 4 minutes to charge your entire battery pack to the full quantity. As I mentioned, the cost of each of these elements play a major role, and that's why I have listed this down. And there is a lot of optimization which is happening on this front, where you want to get each of these efficiencies of each of these elements into your battery, but you want to drive down the cost as low as possible. And hence people are trying to work out chemistries which have 80% nickel, 10% manganese, and 10% cobalt in the research realm in order to really get high energy density but lower the costs of your battery pack. The other side of the batteries, which is the anode material. This is something which is really cool because it has always been predominantly used by graphite. Graphite has pretty much been the material which has been used as the anode, and it is basically because of the layered structure of graphite, where you have lithium which can comfortably be intercalated between these layers. But battery people were not satisfied. They wanted to push the rhythms of this even further. And that's when they started working on silicon anodes. This basically reduces the amount of weight of your battery in order to store the similar amount of lithium. And that is why silicon anodes is being heavily commercialized right now. However, it definitely has a lot of drawbacks of sustainability over years and the cycle life over years, but it is being worked on heavily right now. The future of anodes. This has been discussed a lot in the research realm once again. When you wish to have just a lithium metal anode, wouldn't that be great? You remove off the host element of silicon, you remove off carbon. It's just lithium. And excess of lithium has literally never hurt any battery, especially a lithium-ion battery design. And therefore you would want to have as much of lithium as possible. But the drawback on that front is when you coat it and you strip it, you're having an infinite amount of volume change. And therefore you have a lot of fractures which take place on the anode side, which drastically reduces the cycle life of the battery. Moving further, I've spoken about lithium ion extensively. The one major question which everyone definitely asks is is there enough lithium in order to satisfy the lithium-ion energy demand right now? The global lithium reserve is at 40 million tons right now, and it is constantly increasing as more and more resources and reserves are being found. Even though if it's 40 million tons, the Tesla Model S, which runs about 265 miles on a single charge, requires about 14 kgs of this lithium in a battery pack. Currently, you can have about 3 billion Teslas which can be manufactured into the market. Interestingly, you have only about 1 billion cars. So when we talk about lithium-ion batteries with respect to the electric vehicles, there is enough of lithium for all the cars to function on lithium-ion batteries. But the interesting question gets raised is when lithium-ion becomes the predominant battery chemistry for large-scale storage. Because that's when you would require a lot more lithium-ion within the system in order to be able to satisfy those demands. In conclusion, there is a lot of work which has been going on in the battery realm. The cathodes, the anodes, the electrolytes, and the separators are always being optimized, and the realms of battery chemistry are really being pushed to its extreme. There are different techniques which are being utilized in order to mine lithium, as well as reuse and recycle lithium. There is a considerable amount of research effort being undertaken to understand what exactly happens to lithium-ion when it is recycled, and can the lithium-ion once again be extracted from the batteries which are used and be used into new batteries which are made once again. Or, for example, once the battery dies out in your electric vehicle, can those batteries be used for large-scale storage once again? There is a lot of work which is being going on in this front, and I'm convinced, all in all, at some point of time, the research community will find a way in order to make lithium-ion the most prevalent battery chemistry. Thank you. Yes, please.
Where is the lithium found?
The lithium is found in two forms, basically. You have it as a part of rock metals, which is basically found like just how every other ore is mined. You have it in the form of rocks, or then you have it in the sea, which is in the form of brine, or in salar, which is heavy lithium content water at the underground water tables.
Or where in the country?
Oh, Chile. Argentina is the highest producer. China is once again a very major producer of lithium on both the fronts, and they have been driving the lithium cost market drastically. They have been determining the cost of lithium in the past 2 years. But Chile is one. US has some reserves, but yes, those are the major ones. Yes.
What is the energy efficiency of processing the lithium, whether it's recycled or mined, versus the amount of energy you get out of the battery?
That's an interesting question, actually. So you're basically saying, is electric vehicles really energy efficient, or so-called? So I don't know the exact numbers to that, but I had run a calculation at one point of time, and if you consider the absolute averages of the amount a common US citizen would drive their vehicle, which is 40 miles per day, you should be able to have your car carbon neutral within 3 years of utilization. But you're absolutely right that, up to 3 years, you're technically not carbon neutral because you have put in a lot of energy into the system to mine lithium, cobalt, and all these elements. But post 3 years is when you really are able to get the juice out of this entire process and be carbon neutral. And if you technically look at the way batteries are right now, they are set to last for up to 5 to 7 years. So you have a good 5 to 7 year bracket after to be carbon neutral. So it is definitely an energy efficient process, all in all.